And here's a graph of that same ellipse. One option we can use on the calculator to make it look more like what we intended is zoom square, since this definitely looks stretched out of shape. Zoom square is option 5. We'll let the calculator square its own screen, and what we get looks a lot more like what we graphed by hand. Notice that the two pieces of the graph do not meet. On the calculator, it's difficult for it to shade pixels when the points become almost vertical. You should know that the two pieces of the graph meet and draw them accordingly. We need to move on from ellipses to hyperbolas. I'm going to say the definition of a hyperbola in words and show you a picture as I do. In this picture, the two curved pieces form a hyperbola. A hyperbola also has two foci. Its definition is the set of points, the points on here, such that the difference, the subtraction of these distances is a fixed number. The long distance minus the short distance for any point is the same. Again, we want to put hyperbolas in a coordinate system, and I'm going to show you two different pictures of a hyperbola. Here's the first. This is a hyperbola that has a horizontal axis. Here's the curved pieces, like the previous picture. An important piece of information about a hyperbola is that it has two asymptotes. The asymptotes are found as diagonals of a rectangular box whose width is 2a and whose length is 2b. That shows up in the equation in this way. This particular hyperbola's equation starts with an x squared over a squared minus y squared over b squared equals 1. The equations of the asymptotes are positive and negative b over a times the variable x. Compare that with this hyperbola that has a vertical axis. The axis is vertical. The equation of this hyperbola is y squared over a squared minus x squared over b squared equals 1. Notice that a is the distance from the center to the hyperbola in this vertical axis case, as well as in the horizontal axis case, and b is a distance measured in the other direction. For a hyperbola that has a vertical axis, the asymptotes are plus or minus a over b x. Let's work an example, and as I work through, I'll try to match my example to one of those equations. Here's what we'll do. We want to graph this hyperbola using traditional methods by hand. We're going to state the domain and range, and then we're going to put it into our graphing calculator. Here's what we have. To get one of the two forms in the first case, I'm going to subtract each part of the equation. Excuse me, I said subtract. I'm going to divide each part of the equation by 1,764. This simplifies, and you can check it on your calculator, to y squared over 36 minus x squared over 49 equals 1. This particular hyperbola matches the vertical axis case. Notice that y squared is first minus x squared. That means that the denominator under y is a squared, under x is b squared. We can identify then a as 6, the square root of 36, and b as 7. Let's sketch a graph of this hyperbola. It has a vertical axis, keep that in mind. Because it has a vertical axis, we're going to count a units up and down from the origin, and 7 units, I said a, I meant 6, and 7 units left and right. Counting 6 up and 6 down, 7 left and 7 right, I'm going to draw a rectangle with these points as the boundaries. I draw it as a dashed line so it doesn't get confused with the actual hyperbola. Now the diagonals, which I'm also going to draw as dashed lines, of this rectangle form the asymptotes for the hyperbola. They give us how wide it is. The hyperbola has a vertical axis, so it's drawn opening up, getting close to its asymptote on either side, and opening down, getting close to its asymptote on either side. What we want to do now is see how this particular graph looks on a graphing calculator. Again, in order to do so, I'm going to need to isolate y squared. I'm going to add 36x squared to both sides and divide by 49. So 1764 plus 36x squared over 49. Take the square root using plus or minus to get 1764 plus 36x squared over 49. I need to graph this in two pieces, and I also need to state the domain and range. Let's put it on a calculator first. We have this ellipse from the previous example that will clear, and we'll put in the square root, and there's already a parentheses for the square root, but I need one for the numerator, 1764 plus 36x squared, that's the end of the numerator, divided by 49, and that's the end of the radical. I want just the negative of that, so let's do negative variables, y variables, function y1, just as a shortcut. Now we need to set a decent window. Let's see how this one looks on a standard window. Zoom 6. We graphed it previously, so I knew it went at least to 6 and negative 6 in the vertical direction and 7 and negative 7. This supports our answer by hand. Let's write down the domain and range. Back over here, let's look at our by hand graph and write the domain and range there. The domain is the x's this covers from left to right. Since the hyperbola extends in both directions, that's negative infinity to infinity. The range is a little bit more restricted though. The range extends from negative infinity to negative 6, including that, but then the points in between are excluded, so we union that with 6 to positive infinity. There's one more piece of information I'd like to give, and then we'll do a quick graph. We can shift the center of a hyperbola also to the point HK. And the equations are identical to what we used, but between the parentheses by x and y are an h and k in both cases. Again, notice that the center is HK. Let's do this example. We'll graph this hyperbola using a traditional method and state the domain and range. The center is 1, negative 3, h and k, the things subtracted from x and y. A is the square root of the number under x, and b, the square root of the number under y. Because x comes first, notice that this will have a horizontal axis. Let's draw a sketch of this hyperbola. The center is positive 1, negative 3. The hyperbola extends 3 units left and right, 5 up and down. Here's 3 to the right, 1, 2, 3 to the left, 5 up, 1, 2, 3, 4, 5 down. We'll draw a rectangle. My rectangle extended just a little too far on this side. And the diagonals of the rectangle. And draw the hyperbola opening to the right, whoops, and to the left. The domain of this is from negative infinity to negative 2, including that, unioned with positive 4 to infinity. The range is all real numbers written negative infinity, infinity. In this lesson, we covered ellipses and hyperbolas. There were a lot of formulas. Be sure to do many exercises to practice.